Hello students, welcome to grade 12 chemistry revision lesson on atomic structure and the periodic table. In our today's lesson, we will learn about postulates of Dalton's atomic theory, early experiments to characterize the atom, makeup of the nucleus, and electromagnetic radiation and atomic spectra. Students, if you are ready, then we will get started. Postulates of Dalton's atomic theory. These are the 6 postulates of Dalton's atomic theory. 1. All matter is composed of extremely small particles called atoms, or all matter is composed of tiny particles called atoms. For example, tips of a pencil is made from carbon atoms. Copper foil is made from copper atoms. Gold foil is made from gold atoms. Therefore, matter is made from small particles known as atoms, according to Dalton's atomic theory. 2. Atoms are indivisible particles. We cannot divide atoms further, according to Dalton's atomic theory, which cannot be created or destroyed in a chemical reaction. Atoms are not destroyed in a chemical reaction. Atoms of a given element are identical in masses and chemical properties, according to postulates of Dalton's atomic theory. 4. Atoms of different elements have different masses and chemical properties. 5. Atoms combine in the ratio of small whole numbers to form compounds. If you take water, H2O, hydrogen to oxygen ratio is 2:1. You see, 2 hydrogen atoms combine with 1 oxygen atom to form water. Simple whole number ratio, according to postulates of Dalton's atomic theory. The relative number and kinds of atoms are constants in a given compound. These are the 6 postulates of Dalton's atomic theory. Now, what are the drawbacks of Dalton's atomic theory? 1. According to John Dalton, an atom is indivisible. But atoms are divided into subatomic particles, electrons, protons, and neutrons. The indivisibility of an atom was proved wrong after the discovery of electrons, protons, and neutrons. 2. According to Dalton, atoms of same elements are similar in all respects. However, atoms of some elements vary in their masses and densities. Isotopes are atoms of the same elements which have the same atomic number but different mass number. For example, chlorine has 2 isotopes with mass numbers 35 and 37. Isotopes were not known by John Dalton. Dalton also claimed that atoms of different elements are different in all aspects. This has been proven wrong in certain cases. For example, argon and calcium are atoms, each have 14 atomic mass units. They have the same atomic mass. These atoms are known as isobars. John Dalton atomic theory states that elements must combine in simple whole number ratios to form compounds. However, this is not necessarily true in the case of complex organic compounds, such as sugar or sucrose having a formula C12H22O11. These are limitations or drawbacks of Dalton's atomic theory. Early experiments to characterize the atom. One, discovery of the electron. Electron was discovered by J.J. Thomson in 1897 when he was studying the properties of cathode rays. J.J. Thomson constructed a glass tube which was partially evacuated. That means air was pumped out from the tube. Then he applied a high electrical voltage between the two electrodes at either end. The two electrodes are cathode and anode. Cathode is negatively charged electrode, anode is positively charged electrode. Then he observed rays, bundles of rays, streams of rays moving from the cathode toward the anode. He called cathode rays because these rays were emanated from the cathode and move towards the anode. J.J. Thomson measured the charge to mass ratio of cathode ray particles using deflection in both electric and magnetic fields. Charge to mass ratio of an electron is minus 1.76 times 10 to the power of 8 coulomb per gram. Now Robert Millisian measured the charge of an electron using negatively charged oil drop experiments. The measured charge of an electron is minus 1.60 times 10 raised to minus 19 coulomb. We can calculate mass of the electron from charge of the electron and from charge to mass ratio of the electron. You see, charge to mass ratio of an electron. Charge to mass ratio of an electron is minus 1.76 times 10 raised to minus 8 coulomb per gram. This is positive 8 coulomb per gram. Charge on a single electron is found to be minus 1.602 times 10 raised to minus 19 coulomb. Now, from this mass of an electron equal charge on a single electron, which is minus 1.602 times 10 raised to minus 19 coulomb, divided by its charge to mass ratio, which is minus 1.76 times 10 raised to 8 coulomb per gram. Coulomb will be cancelled by coulomb. We are left with gram, which is the unit of mass. Therefore, mass of the electron equal 9.11 times 10 raised to minus 28 gram, or 9.11 times 10 raised to minus 41 kilogram. Radioactivity and discovery of the nucleus. Radioactivity is the spontaneous disintegration of the nuclei of unstable atoms through the emission of alpha particles, beta particles, and gamma rays. These are radioactive atoms, unstable atoms. They have unstable nuclei. Chromium, radium, carbon, uranium, and nitrogen. 3 types of rays were identified after the discovery of radioactive substances. 1. Alpha particles. Alpha particles are known as helium ion. Alpha particles, helium ion. Helium with atomic mass 4 and atomic number 2, charge 2 plus. You see? Symbol is alpha. Mass number of alpha particle is 4. Charge of alpha particle is 2 plus 2. They are positively charged particles deflect toward the negative plate. Beta particles are known as electrons with mass 0 and charge 1. You see, symbol beta, mass number 0, charge -1. They are negatively charged particles, therefore deflected toward positive plates. Gamma rays, symbol gamma, mass number 0. They have no mass. Gamma rays, charge neutral 0. Deflected and deflected. Discovery of the nucleus. Ernest Rutherford bombarded a thin gold foil with fast-moving alpha particles. You see, most alpha particles pass through the gold foil undeflected. Some alpha particles deflected at small angles. A few alpha particles, 1 in million, deflected either at large angle or rebounds, deflected back. Therefore, Rutherford's conclusion: 1. Since most of the alpha particles passed through the gold foil undeflected, this shows most of the space in an atom is empty. 2. Some of the alpha particles were deflected by small angles. This indicates the presence of heavy positive center in the atom, which Rutherford named the nucleus. Nucleus of the atom contain a positive charge. 3. Only a few particles, 1 about a million, were either deflected by a very large angle or deflected back. This confirmed that the space, the volume occupied by the heavy positive center must be very small. Makeup of the nucleus. The nucleus of the atom is now believed to contain protons and neutrons. Electrons are revolving around the nucleus. Therefore, Rutherford proposed that protons constitute the positively charged matter in the nuclei of the atoms. The 3 subatomic particles are protons, neutrons, and electrons. Particle proton, symbol P+, relative mass in atomic mass units. Note that one atomic mass unit equal 1.660 times 10 raised to minus 24 gram. The actual mass of a proton is this: 1.673 times 10 raised to minus 24 gram. In atomic mass unit is 1. Relative mass of a proton in atomic mass units is 1. Approximate charge is +1. Relative location, proton of the atom is found in the nucleus of that atom. Nucleus. Neutron, symbol is N. Relative mass in atomic mass unit is 1. The actual mass of a proton is 1.675 times 10 raised to minus 24 gram. This in atomic mass unit is 1. Approximate charge, neutron, is neutral, found in the nucleus of the atom. Electron, the symbol is E. Relative atomic mass in atomic mass unit. The actual mass of an electron is 9.11 times 10 raised to minus 28 gram. This in atomic mass units is this. 0.000545. Approximate charge of an electron is -1. Relative location outside of the nucleus. Protons and neutrons are found in the nucleus of the atom. Electrons are found outside of the nucleus. Atomic mass and isotopes. Isotopes are atoms of the same element which have the same atomic numbers but different mass numbers. Most elements found in nature are mixtures of isotopes. You can take hydrogen. Hydrogen has 3 isotopes: protium, deuterium, and tritium. The average mass for the atoms in an element is called the atomic mass of the element. The average relative atomic mass of an element is given by A1 times F1 is percent abundance 1 plus A2 is atomic mass of isotope 2 times percent abundance 2 plus An is atomic mass of isotope n times percent abundance n isotope. For example, the element chlorine contains 2 isotopes: chlorine 35, which has a mass of 34.97 atomic mass units, and chlorine 37, which has a mass of 36.97 atomic mass units. Calculate the percentage of each chlorine isotope. The average atomic mass of chlorine is 35.5 atomic mass units. What do you do? Good. Let's P1 is percent abundance, abundance of chlorine 35, and P2 is percent abundance of chlorine 37, Now, average atomic mass equal A1 percent abundance 1, A1 times P1 plus A2 times P2. Average atomic mass of chlorine is 35.5 equal A1 is average atomic mass of chlorine 35, which is 34.97 times P1 is percent abundance 1, which is P1 times P1 over 100 plus A2 is average atomic mass for chlorine 37, which is 36.97 times percent abundance 2, which is P2 over 100. We know that percent abundance add up to give 100. P1 plus P2 equal 100. From this, P1 equal 100 minus P2. Multiplying both sides by 100, this gives you 35.50 equal 34.97 P1 plus 36.97 P2. Substitute 100 minus P2 instead of P1 in a place of P1. Now this gives you 35.50 equal 34.97. P1 is 100 minus P2. 100 minus P2 plus 36.97 P2. This is the same as 35.50 equal 34.97 times 100 is 3,497. 97 minus 34.97 P2 plus 36.97 P2. 35.50 minus 34.97 is 53. This is 53 equal 34.97 P2 minus 36.97 P2 is 2 P2. 2 P2. From this, P2 equal 53 divided by 2, which is 26.5%. 26.5%. P1 is 100 minus P2. P2 is 26.5. 100 minus 26.5 is P1 equal 73.5%. Therefore, percent abundance for chlorine 35 is 73.5%, and percent abundance for chlorine 37 is 26.5%. Electromagnetic radiation and atomic spectrum. Electromagnetic radiation is the emission and transmission of electromagnetic radiation in the form of electromagnetic waves. The wave properties of electromagnetic radiation are described by two interdependent variables, which are frequency and wavelengths. Now, frequency is the number of times a wave passes a given point in 1 second. See, frequency is number of times a wave passes a given point in 1 second is known as frequency of the wave. Frequency is denoted by the symbol no. Wavelengths. Now this is the distance between two crusts. Distance between two crusts, wavelengths, or distance between two trough. Distance between two trough, or wavelengths, denoted by the symbol lambda, is the distance the wave travels during one cycle. During one cycle, the distance the wave travel during one cycle is wavelengths of the wave. Stream velocity or speed is the distance traveled by the wave in 1 second. Velocity or speed of the wave, C, equal wavelengths of the wave times frequency of the wave. Note that all electromagnetic radiations travel with the same speed in a vacuum, which is 3 times 10 to the power of 8 meter per second. Speed of light, C, 3 times 10 to the power of 8 meter per second. Amplitude is the height of the crust. Height of the crust. This is amplitude. Height of the crust, or depth of the trough. Amplitude, depth of the trough. Electromagnetic spectrum. The range of frequencies or wavelengths of electromagnetic radiation is called electromagnetic spectrum. The range of frequencies or the range of wavelengths of an electromagnetic radiation is electromagnetic spectrum. The electromagnetic spectrum includes both visible waves, the visible spectrum, and invisible waves, invisible radiation, such as infrared, microwave, TV wave, radio waves, UV, X-ray, and gamma rays. Visible light extends from the violet end of the spectrum, which has a wavelength of about 400 nanometers, to the red ends of the spectrum with a wavelength of about 700 nanometers. Vibgyor. This is violet, indigo, blue, green, yellow, orange, red. Violet, wavelengths of 400 nanometer. Red having a wavelength of 700 nanometer. Here it says visible light extends. Yes, an example of visible light is sunlight. If sunlight is allowed to pass through a prism, then we observe 7 different colors. One color merge into the other without a boundary. Vibgyor, violet, indigo, blue, green, yellow, orange, red. See, Vibgyor. Beyond these extremes, electromagnetic radiation is not visible to the human eye. This is electromagnetic spectrum. Wavelengths increases in moving from gamma ray toward radio waves. Wavelengths increase, lambda. Therefore, radio wave has the highest wavelengths, whereas gamma rays has the smallest wavelengths. Frequency increase in moving from radio waves toward the gamma rays. Gamma rays has high frequency, high energy, because energy equal Planck's constant H times frequency. You see, gamma ray has high frequency, therefore has high energy. High energy. Students, let us try this exercise so that you can practice what you have just learned. You have 3 minutes. Good. Let us do together arrange the electromagnetic spectrum regions of TV signal, infrared light, gamma ray, radio wave, microwave, and UV wave in increasing order of wavelengths and frequency. As we said, visible light, infrared, microwaves, TV waves, radio waves. On this side, UV, X-ray, gamma ray. In moving from gamma ray toward radio wave, wavelengths of this electromagnetic radiation increase. Increasing order of wavelengths, lambda. Gamma ray, X-ray, UV, visible light, infrared, microwave, TV wave, radio wave. The question says, arrange the electromagnetic spectrum regions of TV signal, infrared light, gamma ray, radio wave, microwave, and UV in increasing order of wavelengths and frequency. Increasing order of frequency start from radio wave. Increasing order of frequency, new. Gamma ray has the highest frequency, and radio wave has the smallest frequency. Arrange the colors in the visible region of the electromagnetic spectrum in increasing order of wavelengths. Vibgyor. Violet light, violet color. Its wavelength is 400 nanometer. Red, 700 nanometer. Therefore, increasing order of wavelengths is this. Increasing order of wavelengths. Increasing order of frequency from red to violet. Increasing order of frequency. Students, in our today's lesson, we discussed postulates of Dalton's atomic theory. We discussed drawbacks of postulates of Dalton's atomic theory. We learned discovery of the electrons and neutrons and nucleus of the atom. We learned electromagnetic radiation. Electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic wave. This brings us to the end of our today's lesson. Until next time, goodbye.